All right. Good afternoon. My name is Ali Kujuri. For those of you who do not know me, I'm Ali Kujuri, and I am an adjunct professor at the Department of Engineering Science down the hall, and then also one of the organizers of this lecture series on the behalf of our department and the School of Science and Technology. Let me welcome you all to this fourth lecture of this academic year, and also the 91st lecture of the series when we started in 2006. I would like to thank Keysight Technologies, former Agilent Technologies. They are located in Santa Rosa, who have been basically sponsoring this lecture series, and also the department. Before I introduce our guest speaker for today, let me make two announcements. First, there is pizza coming at 5:30, right after the talk. And then the lecture for 2 weeks from now, that is November the 6th, will be given by Dr. Leo Liu from the Engineering, Electrical, and Computer Science Department from UC Davis, and the title of his talk is Radio Frequency, MEMS, and Adaptive Wireless Systems. For those of you who come from the Tech High, welcome. And by the way, MEMS stand for Micro Electromechanical Systems. These are the example of that is, for example, they just make something like a capsule, which is in fact a camera, and then you can swallow it and it can just radiate and give you pictures of what's going on in the body. How about that? Okay. So about our speaker for today, we have Mr. Gregory White. He is a senior research and development engineer in National Instruments, and the title of his talk is Radio Frequency Filter Design Overview, which is going to be very interesting also for our students who are taking the course. Mr. White was born in Chautauqua County, New York. He received a diploma in electronics technology from Sylvania Technical Institute in 1982. From 1982 to 1993, Mr. White worked in the two-way radio industry as an FCC licensed radio technician. FCC means Federal Communications Commission. His work included the design, installation, maintenance, and of advanced and co-located public safety radio and dispatch systems. Mr. White received a bachelor's degree in electrical engineering from San Jose State University in 1997. Since receiving his degree, he has worked as design engineer for Metricom, San Jose, California, Texas Instrument in Santa Rosa, California, and Symmetricon in Windsor, California. Currently, Mr. White is a research and design engineer from National Instruments in Santa Rosa, California, with a special interest in circuit theory and filter design. So here is Greg.
Thanks, everybody. He's introduced me, and I just want to say a word about National Instruments. National Instruments produces a wide variety of test and measurement equipment, including RF signal generators and RF signal analyzers, for example. Some of that equipment is designed in Santa Rosa. Myself, I've been dealing with filters in some way for about over 30 years in my career, and I've always found them pretty interesting, and I am able to combine that interest with my job duties and have an opportunity to delve a little deeper into filter theory. Naturally, for an hour, this is going to be a pretty quick skim over the topic. Hopefully it's useful. It'll be somewhat traditional. A lot of traditional points will get hit, and perhaps a few interesting permutations of my own spin on what I've learned. So just to make a note about the field itself, it's really a huge, massive field. You see the big pile of books you can fall into like a black hole. And it's really, but then it's still just a really small slice of the communications field as a whole. It's one of the oldest theories or whatever in electrical engineering. It started almost 100 years ago. There's really no frequency band in electronics that filters aren't applied to. There's a lot of different methods and technology of providing filtering functions, and it is wide enough that somebody, if they had the right circumstances, they can make a career in just filtering and processing themselves. This is kind of just a quick agenda schedule of what we're going to do. Again, there's much of this is sort of traditional, like I don't want to read the list necessarily. Kind of come back to this agenda that kind of points to just say where we are and all that. Obviously, we're right at the top right now. So moving on, it's like we have to ask a basic question: why do we filter? And the answer is because the electromagnetic spectrum is very crowded. There's transmitters transmitting all kinds of energy all over the place. There's actually unwanted types of signals too. Analog to it, you might think of like a room with a lot of people having conversations at the same time, and so plus noise of some kinds. And so ultimately you want to, if you want to understand something in particular, you have to suppress what you don't want to hear and somehow allow through what you do want to hear. And filters, electronic filters, we design according, by virtue of their shape in the frequency domain. And just as a dual note here, as communications theory people will know, there's a dual in the time domain, and there's like a little comment by Professor Lottie here about correlation in the time domain does correspond to filtering action in the frequency domain. But we're going to focus purely on the frequency domain, and that is usually how filters are designed. So they are used for communication systems, and our basic task as communications engineers is to provide systems and circuits to relay information, to transmit messages of some kind. And involved in that process is picking some kind of transmission medium. It involves selecting a channel, and a channel traditionally means some frequency. We'll speak into a cell phone, it'll be translated to some RF frequency somehow, and then it will be received and then it's transmitted back to baseband where we can somehow hear it with a speaker. So kind of recapping that is that the primary tasks are translation of the message energy to and from the channel, making sure we have enough energy at the very end. We have to have enough speaker volume in our cell phone to hear it, and we have to make sure on the way that the information is not corrupted by inevitable impairments. There's a little common equation right there. Signal over noise plus distortion plus spurious. We want this one big, we want this one small, and the last of these what implies filtering. The top one, which implies number 2, amplify. 3 is filtering. So that's why we do it. So once we decide we have to do it, then we have to decide how we're going to do it. There's a way to classify things. One way is digital filters, discrete filters. They're implemented on ICs and processors of various types, both general purpose and specialized. Let's say nowadays, probably every modern communication system utilizes digital filters somewhere, somehow. And there's no system that doesn't have them, really. Another class could be active filters, which basically means there's some kind of extra power supply that energizes the system that processes the signal. A couple common types there. The discrete filter also, it requires a power supply too. And then the last class would be passive filters, which is our topic today is going to be in this bottom one. And there's a variety of types, distributed, discrete. We'll mostly focus on probably LC and planar today to keep things narrow. We also have integrated forms like SAW filters. And a system in general, it might have combinations of all of these. So they all might be in there. We're going to talk about this, but in general, you're going to see everything nowadays. And as a final note here, passive design what we're going to talk about starts with this so-called lossless presumption. And the lossless presumption basically means that we either let the signal through or reject it. We let what we want through, we reflect what we don't want. The network itself does not dissipate any energy itself. And the reason that's done is basically this idealization just makes the problem manageable, ultimately. It becomes a lot harder the more unideal you make it. And we really, as we go through the process, we will work in the lossy factors as we work through it. But that is a starting presumption. It'll be in every text if you ever investigate this area yourselves. So another way of categorizing filters, some of those texts got kind of skewed there, see that. But, whoops. Another way of classifying them, we have different types of filters. Again, we said that they're frequency domain, and so what that means is this is how much energy gets through at what frequency. A low pass means low frequency energy gets through. High pass doesn't get through. Kind of the opposite here. High pass filter, HPF is the abbreviation. NF is notch filter. The low and the high gets through. Some middle band is chopped out. And then also bandpass filters, where we just pass a band of filters. I kind of have a red boundary around this. I feel this is probably the single most important one, and maybe most challenging, but most rewarding, and most interesting, certainly. So once we decide we want to filter, at some point we have to figure out what kind of technologies we're going to use to perform the operations. And there's, those choices are affected by a wide array of things. What's it cost? Everybody always cares what things cost, right? A filter that goes in a satellite is going to cost more than one that goes in a cell phone. We care about performance, care about the size, frequency range it covers, the fractional bandwidth the technology can offer, perhaps even the weight of it, right? If it goes up in a satellite, what's it pay? And various textbooks or manufacturers, in selecting these technologies, they'll give you various types of graphs or tables and all that. And you have to look at these closely because you're going to have to pick something that works. And of course, these don't have all information. They don't have cost in there, right? But they do have things like Q's in there, the frequency range they use. Fractional bandwidth is sort of implied with unlabeled Q. It's over here, fractional bandwidth. So there's other sources of the same kind of information. We're not going to go through it all, of course, but this is what kind of thing you would reference if you want to, if you need to select your technology, which you will need to. So every text also has something about, like, what is the process of designing filters. I have my own take of it. It's probably correlated with what other people's do. I've structured the way I'm going to present it here according to how it feels to me as I go through the process. And of course, we always start, we have to have a specification because we have to know what we're going to build. And then after we have a specification, I consider that there's three main phases of our process. The first one is the most abstract phase, and in that phase, the first one is find some kind of response function. It's purely mathematical, and actually everything that comes after this whole design process drops down from this. What is possible is actually created right here. So it's a very important and very abstract phase. After we get some kind of response function that is realizable, we go ahead and realize it. That means we get some kind of initial schematic or network out of this. It's usually done by software. We don't do this literally anymore. And then after we get an initial schematic, we might sit there and tweak things around and make it even more realistic as we go through the process. And the key part of this abstract bubble here is this where we have some freedom with what we do. As we go along, things like they turn to stone, right? We don't have that much we can do. So if we want any freedom, it has to happen here in this part. And as much as we can, consider real parts here. Can't ever forget those. Because if you don't consider them, you'll get farther and you say, I can't do it, and you're going to back up, right? So as much as you can, you consider it as you incorporate reality as soon as you can, as much as you can. The next phase is a virtualization phase. We have a schematic. Before we build it physically, we would like to see how it works, and we can use computers and software to do that. Not only can we simulate a schematic, we can tune and play with elements, and we can run automated post optimizers with different kinds of things that drive automatic optimization. We can set our goals that we want, which will have to do with the specification, right? We'll be driving these tunes and optimizing these goals. At this point, no freedom topology. This optimizer, it won't create new parts, won't take parts away. It only permutes on what is already. That's why this point is so important. Then we move to, we actually have to build it. Oh yeah, and we have real parts here, right? Models of real parts. We try to consider it. We're getting more and more real as we go on. Here's where we get really real. We actually have to build it. We might do a PCB layout or whatever. We have to pick parts. We have to assemble it, tune it, measure it, see if our production department can build it. Again, it's in stone. We can't really change in any substantive sense what it is at that time. And these bubbles kind of overlap, because always in a flow diagram, you always said to the past, not where do you go in. So you could be running around these bubbles and probably will run around them to some extent. The less you do, the better, right? That's the holy grail. It's like, you know, and ideally you would just go boom, 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 boom here, and then you'd be done, right? But life's never quite that simple. So moving on here, just give us kind of a where we are here. So now we've said how we're going to do it. We have to create our specification, because we won't know what to build unless we have it. And of course the circuit is drawn out of system specifications. So they're not necessarily the same thing, right? This will be some kind of lesser specification or something that makes this work. But anyways, we'll go into that in a little more detail. And the core issue is to correlate your filter response to what you want to receive, right? Not what, and reject what you don't. So you want to select what you want, and you want to reject what you don't want. It's a fundamental repeating theme we're going to see today. And a filter, you know, should not substantially degrade system sensitivity. And radio work and communications work, right? System sensitivity and signal and noise ratio and all that is critical. And as much as we can, we don't like to degrade that. Always will to a little bit extent, but we try to minimize it. And ultimately, it has to be real. And this might be the same person or two different people, but it's basically a statement. We have to create specifications that are realistic to achieve. Here's the reality, right? This is in every comm book, right? Ideally, we like this brick wall filter. We pass what we want perfectly, infinitely reject what we don't want. There's no transition in between. Immediate response, phase linear is not shown. But yeah, wouldn't that be a nice world? Here's our reality, right? We can only approximate it. We are going to have loss, ripple, finite attenuation. We're going to have a transition band, this little white space in between where it's not even defined. There's responses to go through there. And our phase is going to diverge from a linear response. So this is the first kind of picture of a so-called transmission mask. Well, I guess we saw it before, but it is a mask. This is going towards a specification mask. And here we'll see it in kind of a more busy sense, this thing. Again, here's the primary concerns, what's passed, what's rejected. Normally in most work, pass band loss is the minimum possible. This does not have to be true. There might be reasons to diverge, but it's normally true. And then in this diagram here, wherever's white, this is whatever response function we find, it's got to go through this white. You can go anywhere through there, but it's got to go through it. And this is the pass, so it's got to go above it because it's a gain plot, not an attenuation plot. The blues and pinks are just dividing up different parts of the stop band, saying, oh, in these different parts we need different amounts of the rejection. And the point of saying different is say we don't want to overdo it where we don't have to, because if we overdo it, we've created a more complicated filter than we want to. Things we want to get rid of, just a kind of a bucket list of them. We don't want things from Nyquist zones. We're not sampling if we have an A to D. We don't want images from mixers. If we know of any distortion products, 2x2 that occur in amplifiers and mixers, we want to push them down as much as possible. There might be local oscillators, pilot signals, all kinds of things, other channels. You might know about high energy interferers, whatever you know about, you push down, right? You may not know about everything, but whatever you do, you do what you have to do here. You do as much as you can, given all the rest of your constraints. So I hate long lists, and I'm not going to go through this. It's more of a checklist. basically, I have a checklist like this, whether I'm going to build a filter myself or I'm going to go out of house and have somebody build it for me. I have to define a lot of these things. So I use something like this as a checklist. These are the kind of the obvious things we keep going over, but there's a bunch of other things in here that we do. So I don't want to bore everybody and talk through each of these points. But I use something like this as a checklist, and there could be even more, but those are some ones that show up quite frequently. In thinking about the specifications and noting that the circuit specification around the system, we want to just do a brief little trip into transmitter receiver pair to see how that might work a little bit. So the top one is kind of a contrived transmitter example, although it's not unrealistic. It's a very simplistic diagram. Some message would come in to the left. It would be processed in some way by digital processing. There would be some kind of quadrature modulator here, and we'd be stepping this up in frequency with these local oscillators. It goes on till we get to this RF over here and radiate it out with this little antenna here. And the key point for this talk is we have these filters here, right? On the other end, of course, we have an antenna, we have a receiver, and it's kind of the reverse process, right? Now we're stepping it back down. We have to get it back down to baseband, like if it's a cell phone, we need to get some image on your screen of your cell phone, or we need to get something to come out the speaker so you can hear somebody. But again, we have filters all the way through here. The point of this is that where a filter is might depend on how you specify it. For example, this filter right here, it's after the transmitter and before the antenna. Here's this thing called this link budget in between. Well, whatever loss is here, that directly affects your link budget, dB for dB. Also, it's a transmitter. It might have high power. So how much power can it handle, right? So we want to have low loss and high power handling. That's kind of a given for a filter like that. On the other side, this one is low power. We probably don't need high power handling on this per se, but it comes directly off the link budget, directly off the system's noise figure, right? It's right on the front end before the local low noise amplifier. So loss is going to be very important for this. These bandpass filters, right, we're necking down this. We want anti-aliasing here before the sampler, right? The shape of these is going to be very important. It's going to be dominating. And then also we have to figure, we're combining the response of these in the system. So we don't want to over-specify. The system needs to work. We want to over-specify anything in particular. So here's just a quick example of, like, say we had two IF filters. We have this high IF from the diagram, and then we have the low IF before, say, that sampler in the receiver. Here's the composite of them, right? You can add that up to figure out what you need. So if we had this high IF that just did this, something like this, for example, and this was a design we were working on actually at NI, so kind of some first cuts at some tries. So it's actually a somewhat real experiment in the early stages. But so since this filter's coming down here, right, this green one, we can let it bounce back up here because we just need to get in there. We don't quite make it right here. That was the experiment. Right? It's pretty hard to get there. Maybe go back and say, hey, specification system guy, we're really having trouble. But whatever, it just points out the fact that when you specify the particular circuit, you don't think of your whole system. So let's assume we're done with the specification. We're like masters and we've done it. So we're ready to move into the abstract phase of the design process, that first bubble we talked about on that page. So our general task is to find some mathematical function in frequency satisfying that specification max. Here we have a little cartoon, system diagram. This transmission function is a function of frequency. But here I want to kind of develop just a tiny bit here. What you'll see in every text is more something like this here. We'll have this k-squared factor in the denominator. This is in every filter text, classical filter text. And the key point of that is, as this k-squared factor tends towards 0, the signal goes through. As the k-squared factor gets really large, it doesn't get through, it gets reflected, right? So k-squared holds the zeros of reflection, what bounces back, if you remember the losses, and what goes forward, transmission. Nothing gets dissipated in there, theoretically, or ideally. K-squared, because of all this, it's actually called the filtering function or discrimination function. And it produces these effects by virtue of being the ratio of polynomials. So that's how it's actually done mathematically. Now, we don't really sit there and mess around with K-squared so much. If we're lucky, we get a good software tool from a master, and we just kind of figure out how to steer it. So, but the point is if you remember, I said that in this abstraction, everything falls from this. So, to the extent you can optimize your K-squared, however it's done, by hook or by crook, will control how efficient or how elegant your solution is. So that's why I wanted to bring up this particular point, although it just looks kind of like busy math, but it's, I think it's important. Just to illustrate what I said, this thing on the left is from an author named Minnis. If you know what to do with the K-squared, it just shows you these are all passband variances, and they're just examples of what you can accomplish. You look at these passbands, these kinds of things you could accomplish if you're really tricky. You can do all kinds of weird things if you really wanted to. That's the point, emphasizing freedom. And here on this side, it's the stop band we're emphasizing in this set of graphs. And there's nothing too special. They're just examples from this author. But the point is, in all of it, there's freedom if you know how to take advantage of it. As a counterpoint to that, what's been to make things manageable for a lot of engineers through many decades is their so-called Cookbook Approximations as a kind of a counterpoint to the freedom I just mentioned. And this method made things manageable for people in a different way. It starts with kind of a low-pass prototype that's normalized in every way. So we start with a single normalized approach, and then we convert it to whatever we need. And we get our high-pass, bandpass, or notch filters from that through some various transformations. 3 of the common amplitude-centric cookbook responses are the Butterworth, I call it the Butterworthless, the Chebyshev, and the elliptic filter. The elliptic filter is the most efficient cookbook method in the sense of the order of the transfer function that meets the specification. But Chebyshev is still a very common design also used, and it's all pole. Butterworth, not so much. The good things about cookbooks are there's tools and algorithms available for free. It's covered in every filter book. You just find a lot of information about it. Bad things is you're kind of in a bucket you can't get out. You're kind of, there are some ways to get out of it to some extent, but you are kind of stuck a little bit more than if you understand maybe a more advanced approach. So here's this kind of some schematics to illustrate this point, cookbook versus custom. This is kind of me earlier in my career and then me later in my career. And there's a certain realness. It is contrived, but there is some basis in what actually happened too. A way of, we want to compare them in some way, and so the main point is that they both have 4 coils, because we're doing a compare and contrast. The reason we do that is filter efficiency. One way for LCs is to count the number of coils, really, and that's because we don't like them. We want to minimize them. So the reason is they can be physically big. They have generally poorer than the capacitors. They cost more, and the magnetic fields can cross-couple in ways that are not predictable or that we don't want, that will distort the response we're expecting. We actually have trouble knowing what that's going to be a lot of times. And we have to kind of dig into this. This is a canonical elliptic. This is a non-canonical parametric. But something, if you're savvy in looking at schematics, something you'll notice right away between these is for the same number of coils, this one has 2 transmission zeros. This one has 4. Same number of coils. So, we've got, so the implication is that we have a little bit more power in getting our transmission zeros in there. On this one, we've got a tank here, LC tank, right on the termination, LC tank right on the termination. These are not independent. This resonator is not independent from that, likewise here. On this one, it's not even clear what the end resonator is. It's actually independent. If you'll notice, I've permuted these coil values to very convenient things. These are ones we can buy right off the shelf. The caps, that's not bothered because we can double or triple them up. They're cheaper and smaller, so we don't care about those as much. So those are some obvious things that are the more primitive response and then maybe a more advanced approach. And just to illustrate it in transmission response, here's the power of those extra 2 zeros right here. Just sunk this thing. Whereas this one, it's just no competition, right? Just sunk it. Now, as the order goes up, this difference, the order filter, this difference will be pushed away a bit. But in any case, not only that, we have asymmetry. We have 3 over here and 1 over there. The elliptic, there's always going to be pairs. 1 here, 1 there, 1 there, 1 there. It's going to always be that way. You don't have the freedom. That's the point of the freedom. And parametric has some advantages for LC. Also, every crystal filter is a parametric filter also. It's not, lots of books, I don't even see it in there. It's kind of amazing given how much more it can, given what it can offer us. And so, then you always ask, what networks can your generating tool provide, right? So we pick our tools depending on what they can do for us, right? So that's our approximation part. Now we're moving into, once we have our function, we want to synthesize or realize it. The basic idea is to get a good initial circuit. Probably mentioned that already. And just remember, I did mention this, but the post optimizer does not add or delete parts. It only permutes on what is. So you've got to give it something good to work with. We don't really do synthesis. The software tools do it. The old method was to use tables. I've done that too. Initial realization, I'm probably always canonical, not even usually, which just means it's the minimum number of components for the transfer function, which is not necessarily even desirable, as that parametric filter was not canonical. Yeah, so if we analyze a circuit, we get one answer. It's kind of the opposite. When we have a transmission function, what we can produce out of that is basically infinite possibilities in the strict sense. There will be multiple satisfactory solutions. In a sense, maybe it's as much art as science. You have to know when to quit, know when to be happy, and move on and build it. Obviously, we don't want negative parts. In principle, we can produce negative parts mathematically, but we don't want them really. Software usually takes care of that. Here's an example of a starting circuit and a manipulated circuit. Again, it's a little bit contrived because just for illustration here, keep things as simple as we can. And I want to make the 2-port parameters of these, looking into these terminals, if these were in a black box, through all this operation, we would never know that something's changed inside. And that's kind of the magic of all this, right? So we're able to produce some very different looking things, but yet in the ideal response does not change at all. Here's one thing that was done to it. You can see where these traps are located in this ladder network. They got swapped around, right? So that's a manipulation thing. We'll go into why in a second. Remind me if I forget. Here we have something that looks like this resonant circuit plus trap. We changed how it looks here. And actually the reason for, let's see what we got here. Yeah, so one of the reasons we do this is because we would like to, for example, if we're going to just produce this and never tune it, we'd like to start in our synthesizer with values we can buy from darn near any vendor, right? These are values you can buy. Not these oddball things. I mean, you can't buy that, right? You couldn't buy that. This you can buy. Cheap, right? Low tolerance, cheap. So that's kind of the point of some of these, a lot of these manipulations. Again, the capacitors are oddball still, but we have sort of an advantage that if we're willing to, we can double or triple those up to get close to these odd values. Obviously, this one, the synthesizer didn't really know what to do. It just comes up with this oddball impedance. 50 ohms is a very common radio type impedance. So we, as part of the process, we manipulated this from 92 to 50. So-called hot node absorption to ground. So we went away from canonical here. This is canonical. Now we have a bunch of more parts here, right? It's not necessarily a bad thing. Nature's going to put some capacitance at all of these nodes right here. So how about I beat it to the punch? I put capacitors there by design. Now I can absorb what nature does. If I don't have them there, it's just like, what do I do? Since the optimizer and simulation, we might get it out some, but why not just design it right in from the start? So I'd say at this point we're ready for that process. We're ready to put this circuit into a simulator. And a part of all that toolbox here, there's just kind of a list of features here. A good software tool could probably do all these things in here. These are all your network theorem stuff and just kind of basic circuit theory stuff it does. It's all useful. Use them all, you know. So your tool, if your tool does it, that's really nice. I just kind of got skewed. I guess I have a bigger screen at home. Okay, so I want to diverge in another realization aspect. I want to talk about admittance verge, but very much different from what we talked about. And this has to do with some approximation. And this is very practical for narrow band bandpass filters, or CRF, which I say a coupled resonator filter. The reason this is important is coupled resonators are used in all kinds of technology and things. You can get all kinds of different physical objects that will resonate, and if you couple them together, you can make a filter out of them. So it's a very broad application, and we do a lot of narrowband stuff still today. So that's the reason we're going into it. And if we don't use it, or there's other ways to do these, but we could end up with impractical realizations. And if we do things like this, we can get increased uniformity in our elements, which is always convenient. So first way is the fifth linear element, the gyrator, ideally. So all it says is if we put some impedance over here and we look in here, it just inverts how it looks by the gyrator constant here. That's all it says. You know, same for whether it's a conductance or resistance type gyrator. Active filter theory might go into this a little bit. We can't do that because we can't do ideal gyrators at RF. So one thing we can do is quarter wave transmission lines. It's non-ideal, and it will invert the impedance over a narrower band of frequency. But that's okay because it's a narrow band filter, so we can tolerate that. In LC circuits, we can do a similar thing with pi and T networks. We just put them in here like this, and there you go. Same thing, limited in frequency. Here's an example of an LC one. A couple bad things about this is, whoops, we didn't get our same impedance on both ends. We usually want the same one, so this is a normalized one here. We probably would have wanted one here. Big inductor ratio. These resonators, this resonator is not like that one at all. It'd be nice if they were somewhat more uniform, just out for convenience. So we get our little capacitive, use that version, insert it here, and some equations there. And then we end up with this, and voila, now we have resonators that look the same. If there were more resonators, it would be exactly the same, but they'd be very similar, and we just have a sequence of those in a longer ladder network. Thing they don't always tell you, and one of the reasons I'm telling you is non-ideal admittance inverters affect the pole distribution. We don't have the same pole distribution here as we had up here. Here's the result in the transmission response, right? We had 2 at 0 hertz and 2 at infinity. Putting this thing in, now we got 1 at 0 hertz and 3 at infinity. So it kind of tilted the rejection response here. It actually moved that off frequency a little bit. Going further on the example, not so much with admittance inverters, but as a practical thing, a lot of times we want to control what our coils are, or resonators in other cases. So we'll give a kind of primitive example of that going on with that prior example. So we could impedance scale the entire network, right? There we go. That's cool. Now they're 1 Henry. That's pretty easy. But darn it, we want 1 ohm still here. And that's a problem with conventional. We can't scale these, and I told you that before, we can't scale these N resonators independent of the load. So we can use a narrowband approximation to get around this problem. So standard circuit theory here, right? Split these caps, do Thevenin to Norton to scale it, right? We just pick the right split there, because all we got to do, the right values, split it. And wow, we do Thevenin and Norton, turns these series into parallels, right? That's all we've done. Now, by magic, we're back to our 1 ohm terminations, And we also have we've been able to manipulate our resonators too. So we had some freedom there. There's other ways to achieve this. I wanted to just show this method because here's the funny thing. Now it's a parametric filter. Almost by accident we created a parametric filter. But once you know you can mess with the end resonators independent of the loads, you probably know you have a parametric filter just kind of by inspection. Another pole change with this approximation. Again, we started out with 2, 2. Now we're up to 1 and 5. We have 1 at DC and 5 at infinity. So it's a change sometimes they don't always tell us about. So we want to do some comparison of the responses. The first one was that conventional synthesis, and the one we didn't really like that we started to change at the beginning, right at the beginning here. We're using it as kind of a reference here, this blue one. Next one is this kind of magenta one. We put the admittance inverter in. See how it's skewed it there, right? And we did the N matches again, right? That's quite a bit of skew. I mean, you look at that. I mean, that's quite a bit different, right? So if you had some Chebyshev response in your equation is what N do I need to achieve this? Well, I do stuff like this, and that equation may not work so well. So you have to do it by actually trying to see what you get, which is not such a problem because the software tools make the process pretty rapid. In olden times, it might have been a much more pain, but it's really no big deal nowadays. It's just important to know what happens. This is one that we didn't show. This is a direct synthesis, bandpass synthesis. It's kind of sitting right in there, just for compare and contrast. It's kind of the blue and the red are kind of some idealizations because they're sort of perfect according to the original design in a certain manner of speaking, perfect. So this just focuses in on the passband. Again, you can see these operations did distort it. They're labeled the same way. Our ideal ones, this bandpass and this I one here, they hit right exactly where we defined our right there, and right there. They hit right exactly where we said our band edges were supposed to be. The ripple is exactly 0.1. These other ones got distorted by the operation. It's not that big a deal because finite Q is going to wash out a lot of this, and our optimizer will pull this back in eventually. So it's not that big a deal. It's just important to know what happens. So if you want to know some tools, some I've used here, one's called Filson. This is one of the giants of filter theory and CAD tools. He started his tool in the 60s. He's retired now. It's not under development anymore. It's kind of for experts. Actually, to do this, if there's ever a class, do that. And here's something students like, wow, we got one of the most powerful tools in the world is now free to use. It is a little difficult to use. It can be quirky and crash. That said, the price is certainly right. One of the best tools there is. I also use this New Hertz by Jeff Kaler. Has some of the same capabilities as above. Does this distributed cross-coupling thing. That's nice because we get these arbitrary stop bands with this in coupled resonator filters. So that's a good feature, and this is under development. So this is good here. It's not free, kind of expensive. I'm not saying that's wrong. It is what it is. iFilter is a tool that's built into our own AWR microwave office package. It does distributed and LC synthesis. It doesn't do manipulation. It does have excellent integration. If all you need is a cookbook filter, it's a perfectly good solution. So yeah, we realized it, and now we need to go in and see how it's going to work in the virtual phase. So we're going to construct this network virtually. We include every single element that we put in the synthesis manipulation, and we include any parasitic elements we can think of. For example, if it's on a PCB, right, we got trace, things aren't zero, things are really distributed always in the real world. So we have lines and traces. The components sit on so-called copper pads, which will have capacitance to ground. So you put all that stuff in, or certainly anything you think could possibly be important for your frequency operation. Models is always a big question, you know, how good are our models, right? L isn't an L, a C isn't a C, nothing is quite as it appears. So we need things that are a little bit more advanced than that to get realistic results at this virtual phase, so that when we build it, hopefully we don't get too many big surprises. You know, we might have to actually make our own models and our own library of elements that we place in our schematic. It could come down to that. We buy some models from a company called Modelithics. They do very nice microwave models and all that. It's the best we've found so far. Integrates with our tool pretty nicely. Then of course we simulate it, we tune it, optimize it. We put our specification mask goals in the optimizer, click the button for the optimizer, and sit there and wait, you know, make that all those neat mathematical algorithms that the software masters have created and drive our circuit towards what we need. We'll also do maybe some Monte Carlo to see how it might vary with various kinds of temperature, tolerance, whatever. And the simulators have their own levels of abstraction. So, you know, we could be circuital, right, which is certainly an abstraction of Maxwell's equations. Planar might use a so-called 2.5D or up to 3D. Of course, as you go from in this direction, right, from circuital to 3D, the computing horsepower gets a lot, the demands become a lot higher, and of course it becomes more complicated. And of course, your answers are better too. So it also might be linear or nonlinear. For us, for most filter work, we use linear filters. Just a quick picture of Microwave Office. A colleague put this into Microwave Office. This is a real filter somebody built. I did all of the abstract phase work for him. I created the initial schematic. He put it into Microwave Office. And you can see, even though it's an LC filter, you can see little transmission lines in here too. It's hard to see, but he's putting those parasitic things in there as much as he can think of, and you know, tries to make his schematic as real as it can possibly be. This is just kind of a graph of what he's done. And the system's in there too. He's got, like we mentioned, the cascade of the receiver. He's actually, in his total system here, he's got earlier filters in the system cascade too combined, because he wants to see how they all work together. In fact, he's really driving his optimization goals according to the system needs, not the particular filter. Like the filter better be good or else it won't meet it anyways. But he's doing pretty good. He's done some changes since then too. But it's just an interesting example. These kind of hash marks are the optimization goals. They're going to relate to the mask in some way, the specification mask. And there's the actually system mask actually. Before the A to D, right? He wants to knock this stuff down E to D just because of the performance of his A to D, right? Don't want to waste the performance of the ADC, right? So he's got to push all this unwanted stuff down. I want to just talk about a couple little practical problems that always come up. I mentioned it before. First one that's always a deal is finite element Q, right? Things aren't really lossless, even though filter theory sort of likes to pretend they are. The effects of this is it will reduce the bandwidth from the native design. Can cause insertion loss that could affect sensitivity. It reduces the relative rejection. Whatever this insertion loss is in the passband, it's probably going to reduce the relative rejection by that amount. Passband could get distorted, so depending on how important the shape really was, it may or may not be a factor. You might go, you're probably going to have to tolerate some in the real world. And it sets a practical lower limit on the fractional bit bandwidth for whatever technology you are using. Another thing that bites this is element tolerance and no tune. And all I mean by no tune filters is if our production line, you know, is the printed circuit, it's assembly being manufactured, it shoots the chips onto the circuit board, and all I'm saying is after it shoots them on there, we don't tune it, right? It has to be right to start with, so that kind of requires a good design, it requires good tolerances, but it will have tolerances, and those can bite us. And kind of these first three things is where, you know, for the pass band, the stop band, and return loss and importance, but we'll need excess margin in our specification that are designed to handle these kinds of effects. And just like Q, it can set a practical limit on the fractional bandwidth that can be achieved. And then much of these things, we might have to, since we need extra margin, we might have to increase the filter orders. So, that's how it affects us in a real way. We might use better parts for this. First thing you say, why didn't I use them in the first place? But maybe if it's a virtual stage, you will use them before you build it. Let's just go an example of this. This is 4 different fractional bandwidth filters here. There's something constant about all of them, which helps the compare and contrast. They all have 3 resonators. The Q of the resonators is about 40. The design ripple is 0.1. Just as we can see the 2% filter. There's 17 dB of loss in that thing, just because of this Q, right? And that doesn't talk about the bandwidth. That's just the Q. Just the center frequency insertion loss is degraded by that much. A bunch of points there. You can read them if you want, but I just want to point out one since we talked about it. For example, this 2% filter. If we wanted to get that, we want to pull that up to 3 dB of insertion loss. We need a resonator Q of 260, right? Much higher than this 40. So Q of for LC filters, right? It affects the bandwidth available. Probably 2% is about what we can do. 260 is pretty good for a coil. In some cases, it can go higher. Sometimes you can't get that much. For resonators and printed filters, right? That's a pretty darn good number. Often it won't do that well. It won't do that well. So these things affect what we can do. Another example of losses. Here's an 8% bandwidth filter. Another a little bit contrived, but it does illustrate the points. It has 6 resonators. Q of the resonators is 70. Same design ripple as before. Right away, there's 7 dB of loss, right? Just because of this Q. That's not a lot of resonators, really. But it can hit us, right? So that bandwidth gets narrow, boy, it pushes that thing down. 3 dB bandwidth, it's down 20% from the native 3 dB bandwidth. It's even 13 from the 0.1 dB. I almost design according to the ripple bandwidth and assume that, and think about the 3 dB according to that, because this one is just so out of control, right? 3 dB bandwidth is not really too important natively, in my opinion. This one's always important. As what we get, it's important, but not native design. The return loss is affected too, right? These points on these markers. I would say an optimizer might pull this up, though. You might actually be able to fix this to some extent. We talked about it, 7 dB of insertion loss. When you look at the rejections, it doesn't really matter, right? It's not affecting the rejection, the Q, because it's dominated by the reactance of the components, not the loss of the component, not the resistance of the components. So it's about the same. So basically, the loss of rejection is the amount of insertion loss, basically, or even worse if you compare the quantity. So it's almost 1 for 1. Not quite. There's a little bit of space, but it's almost 1 for 1. Element tolerances. These are some pretty simple, contrived things. Worst case-ish, just to kind of do it. So this one, in some sense, it's sort of randomness, right? They're going in different directions, right? So, and we give the worst case example. I would say the passband is not degraded that much, and Q is probably end up smearing all this stuff out anyways, or being dominant over this. I would say that part is not so much a big deal. Return loss definitely got affected, right? It's supposed to be down here and went way up to there, and it's narrower, so it does affect that. Return loss is quite sensitive to tolerances. Here's another where they tweak them both the same direction, right? Which may happen, right? We've got similar resonators that are coming off the same production line at the same time. It's possible they are not some kind of uniform distribution. They might be going off the same way. So worst case is not that bad of an analysis. It sounds like kind of pessimistic, but it may not be all that pessimistic. It harms pretty much everything. So going back to the previous point, we'll have to design extra margin to handle these kinds of effects. And anyways, this is just to give an example of it. Some of the filters we do at National Instruments, just out of interest, we do inductor capacitor filters, 100 years old. This technology is still going strong, and no chance of going away. We do them mostly in this range. the range of LC filters is really actually much wider. We do both in-house design, and we end up purchasing them also, depending on what the needs are at the time. We use surface acoustic wave filters. They're physically small, have a low profile, low fractional bandwidth that we could not achieve with any kind of in-house design. Their cost is moderate. They're sort of IC-like. Here's the frequency range. You'll see, again, we purchased them. I don't know if I said that. We use ceramic microwave resonator filters. They're moderate cost. We always buy those. This is roughly the frequency range we would be using. We start to get big below that frequency. Probably start to look at other technologies like LC below that, right? 1 gigahertz, 1 gigahertz. We use planar type designs. They're distributed in nature, printed, both strip line and microstrip. Probably strip line more often, but sometimes microstrip. They're zero cost as far as dollars because they're part of the PCB fabrication. They do take up real estate. In fact, one of the reasons we don't go down too far, right? Because the real estate gets bigger as the frequency goes down, right? So we have limits. So I'd say contemporary, we're using sort of in this frequency range, and those are always in-house design. We also use this type of device, a so-called YIG-tuned filter that stands for yttrium iron garnet. So YIG-tuned filter. They're dynamically tunable for the user. They can use them in frequency sweeps. For example, a spectrum analyzer will sweep across the frequency spectrum, right? So this type of filter can move with it and block out things. So they are useful. They're very expensive. We would call them large from our perspective. It causes the need for extra RF cables and connectors. They're power hogs. We have heat we have to get rid of because of them. They're good from the low gigahertz and the tens of gigahertz range. Obviously, they're purchased. It's a very highly specialized type of filter. Here's just I can't take a picture of this filter because it's internal. It's strip line internal to the PCB. So I just went into the so-called PCB artwork or layout. You can see I didn't do this. Another engineer did that. See all kinds of. So it's like, can you spot the low pass and band pass filters? I know one person in the room can spot them, but. Yeah, so it's kind of interesting. The colored part is the copper, and the white is where there isn't copper, basically. So this will be one of the internal layers of the PCB, and then there will be dielectric around it on either side. In fact, the layers of copper are, there's multiple layers of copper more, but we'll be clearing out multiple layers. So they do take up real estate. They can be very challenging, and that's just to fit them in. You can see how he's twisting around because he had to get circuits around on other layers of the boards, right? He said twist these around so you can just even fit them in. It's quite a challenge. It's kind of impressive. More of the same guy. You can see the scale inch there, maybe a half an inch right there. We had him on the previous one. More of the same, just kind of interesting. You've seen it before, but kind of interesting. Here's an LC filter. No tune. Again, the production department just shoots the chips on there and it ends up working. It's an in-house design. It's these inductors as we go along here, and then all these little capacitors that hook it together with the traces and all that. COTS means commercial off-the-shelf, right? Parts. We just buy them, stuff them right on the board. There's a little bit of a surprise in this one. This was a Rev A board. Had this transmission 0, right? Didn't have this in the simulator, didn't design it in. It's like, this is life, right? You find these things, not necessarily harmful, but we tend to not like surprises anyways, right? This is the old question about modeling and simulation. How good are our models? How good are we anticipating things we don't know about? Mitigate in the next revision. This is actually, this cross-coupling, right? It's basically saying like this inductor's hopping over and coupling to this, and you see what I did there. Their orientation is the same, so that's probably a mistake. Same with this, right? These magnetic fields here. I don't know exactly which ones are doing it. Maybe they could all be doing it, but that's the deal, right? When I did the next revision, I kind of did some offsets and turned things around a little bit, but yeah. So we don't like surprises, and we still learn things as we go along. Oh yeah, so. This is about an inch right here, just to give you a scale, that's an inch. And then we're going to look at this, the inside of this, that's a filter. Here it is, I took the sticker off. This is a purchased one. It's an LC filter also. Kind of looks kind of ratty in a sense, but it works. The company that builds them, right, they got these little holes in here, and the technician on the assembly line will go in there with a little tool and poke around and push those windings around to change the inductance. That's how they actually tune this thing. Seems kind of primitive, but that's what they do it, and they get lower bandwidth than we can do with the COTS parts. I mean, that's the whole reason we bought this instead of doing it ourselves. And this kind of goopy red stuff, right? All that means is, in fact, there's a PCB here. It's on this PCB mounts on ours, and they got an extra little PCB along there. We can't really look at it there. We got capacitors. They solder it by hand there. But this red goopy stuff, that's after they finish pushing these wires around, they just put this goopy stuff on there, and it kind of stakes the coils so they don't shift after they've been tuned. That's why it looks so messy, but apparently it's effective. We don't really have problems with them. This is how the SAW filters look, kind of basic PCB, maybe a little bit of a boring picture. They do have small footprint. See, those are tenths of an inch there, so you see how big they are, right? They look like IC sort of. It is an IC-like process, actually. We've talked about what SAW filters can do. Here's, we won't go through these points. We buy these ceramic filters too. Here's just kind of a potpourri of some different ones. They can vary in size quite a bit. This is kind of huge one at 914 megahertz. Here's a monoblock down at almost 6 gigahertz made by a Japanese company. Very cheap, high volume stuff. Here's one we bought, right? Here it is there. Here it is tilted. This is on one of our boards. Dielectric filter. That's the low pass prototype order. 1, 2, 3, 4, 5, 6, probably 6 order low pass prototype is what was in this. Here's a cell phone die. I don't know. I found this online somewhere. It looks damaged, right? The silvery conductive coating has been ripped off. Somebody's taken it apart. But it's very exotic looking inside. So some filter expert designed that thing, right? Probably very low cost, but it's kind of a look at that and say, boy, I wonder what's inside there. Really interesting. Here's how the YIG works. This is one of our assemblies. It's this giant thing in there. This is why I don't like it, right? It cuts a hole right through circuit boards, all that. It's really just, we don't really care for it. But it does a good job, so it's life. We're probably just whining. Up to 25 watts of power that thing consumes, right? It's got heat sinks because it has a lot of heat, so it's got to go away there. Here's a different view of it right from the top. Just gives you a view of how it cuts through the entire assembly. Kind of at the last, about at the end here, so I did emphasize this, can we get away from Cookbook? Can we have freedom, right? Because it makes our circuits more elegant, our networks, to the extent we know how to take advantage of that. This is an ongoing process always, right? Improved modeling and simulation, because this is it. This means, the less we have to mess with it, right? We like to sit on our butts in our cube and just work the computer, and then we build it just like magically works. It never happens, but that's our holy grail, right? That's what we want. That's what we always seek. So this is a process that will continue. It's definitely improved over the decades. I'd like to see more of this in our coupled resonator design for our planar circuits, for our bandpass filters. They would be more efficient, possibly take less space. Remember I talked about that? So there might be some discrete application. I'm not so sure about that. My experience is that element values become kind of unmanageable. But certainly for this, we do see, though, that we see these people doing these designs. And we haven't done so much. But I see a big future in improving both the tools for writing this and the ability for regular engineers to do these kinds of designs. Build the YIG, right? So expensive and big. So you got to talk, probably maybe not quite the same subject, but you got to talk on RF minimums coming up. That might be experiment. So you wonder, is this a way to solve this problem? It's like kind of up in the air, but we'd like to think so, right? We don't have to get rid of 25. We don't have to supply 25 watts and then get rid of 25 watts of heat. this kind of pine. We're not really working on this. Suppose we had a production tunable filters that we wouldn't have these COTS tolerance requirements at the beginning, right? We have some kind of software algorithm, maybe some kind of robotic thing that could do all this, or something that could solve this. Not really working on this per se, but it would allow us to do more in-house, I guess, and go out less, right? Puts more power in the circuit board designer's hands. And that's all. This is a filter I did, so that's what it was on the previous one. So that's all I got.
Okay, can I ask? Does anybody want to ask any question?
Do you have any sort of advice regarding the transition from simulated component values to like reality?
Well, yeah, that's kind of the thing is, I mentioned we do get, we actually purchase software from a company named Monolithics, and their whole purpose in life is to give us good models and simulate reality. And it is the holy grail. How well do we anticipate these things? Ultimately, if we either have problems based on experience because it didn't work out, or anticipate, so we can go and actually measure a component ourselves too before we incorporate it into a design, right? It's not that easy really, because in the RF world, right, nothing's zero length, and we have to de-embed results and all that with math and all that. We need professors to help us with all this process. But yeah, so it's that's part of my holy grail comment, right? Getting good models or other aspects and making higher levels of simulation up to 3D and all that, make it easier for us, right? Because even, I mentioned like the coupling of coils from one to another, right? That's not even a single component, right? That's an effect of joint components, right? How about we enclose it in a little cavity, right? Now we're radiating energy into this low loss cavity. What's that do, right? But that's not even a component that's in schematic. So we do have all kinds of challenges in trying to simulate and get good models of what we're doing. It's, the better job we can do with that, the better chance we have no surprises when we put the real parts in there. Good question.
For the design projects and so on, the student would like to use the RC filters, especially in the lab and so on. Now, what are the limitations of the RC filter with respect to the LC or RC?
Well, I haven't focused myself on the RC, the active filters, quite so much. I mean, probably the main limitations are the amps you use themselves, the operational amplifiers, and those are probably getting better. I think the one thing about the LC filters that is nice, it doesn't have any linearity requirements, right? It's very, well, I suppose if you have a ferrite core inductor, it could saturate and things like that, but a lot of our frequency band, they're air cores, they won't saturate, they're very linear and all that. You have noise figures of op amps and all those things, so I would say in certain ways the active filter is got its, it's definitely got its complications, but you'll never get up in frequency like you can get. So this is RF filters, this one, but yeah, I have done some active work, but we don't end up doing it that way usually for our RF. It just does not perform well enough, frankly. Even LC just outperforms it. So.
You are saving for high frequency, but then for low frequencies that some of our students are using, they would like to use the RC and activated RC.
Well, you have to look at your components, particularly your capacitors, right? The capacitors, you get all kinds of bad capacitors at low frequency, right? So the capacitors can be pretty poor too, so you have to watch what capacitor you put in there. Look very closely at the specifications of the capacitor, right? I mean, some capacitors, right, the capacitance changes depending on the voltage on them, right? So you don't really want it, right? That's a nonlinear effect right there, right? You don't want that. Yeah, they might drift badly over temperature and all kinds of, and you really have to select good parts and have good filters also. So, and it's got extra challenge, right? A passive filter will never oscillate, right? It's never going to oscillate. It has no stability concerns or anything. You use an op amp, right? You've got to do all your stability analysis and all that. So in some ways, it's its own every area has a lot of challenges, right? And everybody's pushing their frequency range or their linearity and everything. So every single area is something you can expand greatly.
Yeah, it might have been said at the beginning, but how long have you been working in this field, RF field?
Since my first job was in 1983, actually where I got paid to do some kind of work with electronics and radio. And, I was a licensed technician at that time, so I went directly into radio work. So I was working with filters really from day zero, in some fashion. And it's been since I've been an engineer that I've really designed filters, which is since 1997.
Yeah, you design filters for your own equipment or for other people?
No, it's kind of you got the dime, I got the time type of thing. I am very interested in it. I do study it a lot, right? I mean, a lot of what I've learned, I'm basically self-taught pretty much. So it's not like I haven't done a lot of my own work and investment, right? Anything that I know that seems a little bit unusual in what we've done, I've basically taught myself. So I don't necessarily build them for that reason. I mean, we have plenty of reasons to build them at work. So, you know, I get my fill of actually doing them. So, yeah, I kind of use my personal time to get all my background solid, right, as solid as I can get it. It's very challenging field.
Okay. Seems that the pizza has arrived, and on the behalf of our partners, I would like to thank Mr. White, who really gave us a very good presentation. It was very instructive for me too, because I'm working on this for some time. So let's just give him a hand. So can I ask you to just start with one slide first, and then go with the next one, because soon they disappear.